So, welcome back to the White Box stage. Hi, hi, hi. Yay, we're seeing an almost full house. And I hope we are going to have a full house because the next one is going to be really, really interesting. Why? Because the world is full of complex problems, right? That would benefit totally greatly from machine learning. Think of problems like drug trafficking or race problems. So there's all these things. However, in many of these cases, the people who have the most domain expertise do not really have the technical skills to be able to build a machine learning tool. Solution on their own. So next up, what we'll hear about is an interactive do-it-yourself tool that allows a user who is not a data scientist to train and deploy a classifier by herself or himself. So next up, please welcome Shai Hertz, algorithms team leader at Refinitiv, to the stage. Please give a big round of applause.
Thank you. OK, hi. Thank you very much. So I'm here to tell you about a text classification do-it-yourself tool that we developed and share some lessons that we learned. And I hope that you will find this valuable. So let me start by saying a few words about Refinitiv. So Refinitiv is a new spin-off company that up until a few months ago was Thomson Reuters financial and risk business unit. And what it does is provide data to financial institutions such as banks, investment houses, regulators, etc. And the data could be roughly divided to structured numerical data such as prices, quotes, estimates, and unstructured data, which is mostly textual. And this is news from Reuters News, but also thousands of other news providers, broker research reports, stock exchange filings, and more textual data. And basically, what we want to do is help our customers find the most relevant data for them. So why do we need text classification? As you can understand, we have huge amounts of textual data. Only news is over 10,000 documents a day, only from Reuters, actually. So multiplied by thousands of news sources and other data providers, and really you have overwhelming amounts. And also, our customers have very specific and very different needs. So they come from very diverse backgrounds. They work in different sectors or subsectors. And our data experts have come up with different taxonomies so they can address the specific needs. So if we take a look, so we start from this very general scheme of markets, business sectors, geographies, etc. But then if we dive down into markets, we have this commodities, currencies, debt, equities, and inside commodities, we have a different range of commodities, and we can dive even deeper inside and get very specific topics like solvents here, or like renewable energy, like hydroelectric power stations at the bottom. So really, it's very, very specific, very, very detailed. And I think you can try to understand that if I'm a customer who is interested in solvents, then getting me a news story talking about new petrochemicals regulations in the European Union is something that would be very relevant to me, but it's very hard to find. So I need to have very specific solution for my needs. And since we have these huge amounts of data, we don't want to do some manual labeling and classification of them, and we want to do it automatically. So this is why we need machine learning to the aid. And as I said, we have hundreds of classes, and also each document can belong to more than one class because they talk about more than one topic, or they address different aspects of the topic. So you can ask yourself, isn't this already a solved problem? I mean, we saw some different APIs that you can use, upload your data, get text classifier. If we look at academic benchmarks, like the one that you can find in NLP Progress, then you can see that the error rates are very low, and you think, OK, just take something off the shelf, train your model, deploy it, and you're done. But then the problem with these academic benchmarks, and I think this is also related to what Vered talked about earlier, they have very specifically defined problems. So they work on very few topics, not hundreds of topics. And they work on mutually exclusive topics. So for example, in the AG News problem that we looked at, you need to classify news to 4 different topics, but they are business, politics, sports, I don't remember the fourth one. And also they have huge training sets that are already existing. So if you want to build a new data set for a new problem, you don't really know how to do it. And just to look at something from one of the academic papers, so this is from the ULM Fit paper, you can see here the number of classes that there is for each one of the data sets. So there are 6 data sets, and the biggest one has 14 classes, again, very far from the thousands that we have, and the number of examples in the training sets. So you can see that their data sets are very big, and this is not something that we always have for our problems. So what do we want to do? We want to build a tool that allows content experts to build machine learning text classifiers. Why do we want to do it? To give content experts the power? Because they have the expertise. They know exactly what the topic is about, what documents belong to the topic, and what documents shouldn't belong to the topic. Also, it's more scalable. We have more content experts than data scientists. And frankly, after doing the first few topics, we don't really need data scientists to do it. We can try to automate this process. So this is the purpose of the tool. And we have 3 requirements from this tool. So it should be comprehensive. And users should be able to complete the full pipeline, start from create a training set, train the model, evaluate its performance, do some cycles of improvement, and deploy it to production. So it could classify documents in runtime. It should be friendly. Our users are not data scientists. They're not even programmers, so they don't know how to code. They don't have technical skills, and this should be something that they can use by themselves. And as I said, our problem is that we have very sparse topics, and this is, I think, something specific for this problem. So let's start at the very beginning. We need to have a corpus. We need to have a large body of documents from which we can select our training data. And this is one of the lessons that we learned. It should resemble as much as possible production data. So I don't want to stay too long in this slide, but we want to sample a whole year of data so that we can overcome some seasonal effects. We want to separate the train and test and make a hard split here, based on time, so that we don't have any data leakage. We want to do some cleanup, to clean boilerplate, again, so that our classifiers don't pick on the wrong features. And do some deduplication so that we don't have over-representation of the same data. And then, when we work on a specific topic, we need to have positive and negative examples, right? This is the very beginning of training a machine learning classifier. So we have a textbook solution, just sample data, start to say this is positive, this is negative, this is positive, this is negative, but this is not something that you can really do for our kind of topic. So if you have 1 positive out of 1,000 documents, then the user will be overwhelmed if they only need to come up with 100 positive documents. So this is very, very not user-friendly, not feasible, and not something that we can do. So what did we do? We asked the user to help us. Again, remember, they have the expertise. They know what the topic is about. So we asked them to define a query and search documents where there is a dense representation of positives. So in our big corpus, there is a very specific query, and they should start working on this. So, for example, a topic that I'll start talking about is a change of CEO. Again, a business event which is very interesting to financial customers. So we want to have words like CEO, near, nominated, or resigned, and not something that's irrelevant, survey, or opinion. So this is something that users can build very easily, can define very easily, and this could, at least potentially, bring a lot of positive documents and not too much noise with it. But again, we have a problem. So if we want to cover all the positives or most of the positives, we need to build very detailed queries. They need to cover a lot of options. So if I said that we want most of the query documents to be positives, or not most of the query documents, but a lot of the query documents to be positives, then we get something monstrous, like this query. So we can see here that after doing some iterations, the user understood that CEO by itself is not enough, because sometimes the CEO appoints people, so you want to have as CEO. And then they added some different morphological ways to say resigns, or resigned, or resign, or resignation. and you have a lot of and not to filter out noise. So just looking at such a query is very unpleasant, and let alone building it and making sure that it compiles, that the grammar is correct and all the parentheses are in place. So one way that we can help the users is through user experience, UX. So we have a visual tool that helps the users build queries. So this is probably too small for you to see, but we divide the query to clauses. And then the users can define within each clause different synonyms. So we have on top replace, resignation, appoint, step into, promote. So these are all the verbs that describe the change, either resignation or appointment. And we can have different rules for CEO, chief executive, and define some logic between these rules. The other aspect of the solution is algorithmic. So we suggest additional terms so that the user doesn't need to come up with all the different ways to express something. So we have synonyms coming from Word2Vec, which I hope you are familiar with. Vered talked about it, Navid talked, and I can talk about it later if there's interest. Some morphological expansions based on just using dictionaries. So basically we have appoint, so we look at appointment. And another thing is looking for words that tend to occur with the query term. So we look at the documents, we find words that appear there quite frequently, and we should suggest them as well. They're not necessarily synonymous, but they could be related to the topic. And again, we suggest them to the user. They can accept or reject, but at least he or she has the information. So this is what the suggested terms look like. After that, we have documents, and we have the tedious part of starting labeling the data. So this is what the UI look like, and we'll go back to this in a second. But a lesson that we learned and was very, very painful is that users don't want to read long documents. And you ask them to read all the documents, not to skip documents, and you discover that they didn't read or that they skipped. And even if they think that they read the whole document, they actually didn't really focus on everything. So this is something that you really need to take into account when you work with people and not with computers. And our solutions to this problem, again, come from the user experience realm. So we have an option to save for later. So we don't want the users to skip, because skipping introduces bias into the data. So if the machine never sees long documents, then it can't learn anything about long documents. But we allow the user to save a document for later, so they can ask their boss for help. They can make themselves a big cup of coffee. They know what's ahead of them. And another thing is highlights. We allow them to focus on specific parts of the document. So if I have here this long documents, but I'm only interested in mentions of CEO or Chief Executive Officer, then I can just highlight these phrases. The user can focus on them, read the relevant sentences, and make the decision. OK, so we have our positive examples, our negative examples. We can train a machine learning classifier. Well, not exactly. So the query didn't cover all the positive documents because we wanted to have a high ratio of positives. So how can we make sure that our coverage is good, that the recall is good? We identify terms that cover all the positive documents, and we build very simple rules. Just if you have one of the terms, then it's enough. Then this document can be a candidate. And this is done using a significant score. So basically, we compare the frequency of this term in the positive documents that the user already labeled and compare it to the corpus. So what we have here, for example, we have the term or the word pair new CEO, and in 2 million documents in the corpus, it appears 1,000 times. But in the positive documents, we have 46 out of 200. So this is very indicative, and this is something that we can use, which wouldn't bring back too much noise. And we just identify terms that will cover all the positive documents. So what we get is something like this. So basically, we have the query, which had high ratio of positives, but didn't cover all of them. And we introduced these triage terms that cover all the positives, or hopefully cover all the positives, but have much more negatives in them. But then the user already labeled documents, so we don't ask the user to relabel, and we'll see later how we deal with this noise. So these triage terms have dual use. We can use them to expand the training set, which we'll see in a minute, but also they're useful in runtime. So if we apply this filtering on documents, then we can completely filter out irrelevant documents, and this could save us from embarrassing mistakes. And this is also something that's good for latency if you implement it properly. So I said that we want to enlarge the training set so that really the machine learning algorithm sees the most broad aspects of the topic. So we have here the triage, the documents in the corpus that have at least one triage terms. As I said, it's usually wide. It has a lot of negative examples. And we have the query, which is very specific and contains a lot of positive examples. And if we look at the triage minus query, so this is the white area, most of it is negatives. It has some positives, but the probability of being positive should be pretty low. So we can just add some documents, sample from this area, and assume that these documents are negatives. And then we make sure that our training set really covers all the documents that we will need to tackle in runtime. And as I said, that we also use the triage in runtime. So basically what we want to make sure, and I think I also mentioned it in the corpus, is that our training data resembles our runtime data. So we now have data. We have manually labeled positives and negatives from the query. We have heuristically labeled triage negatives. So we have a few hundreds or even a few thousand documents in this set. It has some noise, but we can try to deal with it later. And now the user can press a train button and get a machine learning model. We use SVM, support vector machines. Basically, it's a linear model, pretty simple. Until 10 years ago, it was the state of the art, but in the academy moved since then. The big advantage of it is it trains very fast. It's very easy to understand, and it doesn't need a lot of training data. I'll talk a bit later, if we have time, about a deep learning alternative to SVM. And then, as I said, we have the noise. We want to know, can we improve the results if we just do some cleaning? And this is, again, where we ask the user for his or her help. We ask for feedback. So how can we turn mistaken negatives into positives? And we already have a classifier in hand, so we can use it. So we have this iterative process. We run all the documents, give them scores using our classifier, and sort them from the highest to the lowest, and then ask the user to go over the top ones, which he or she didn't label before using the query. So just say, is it positive, is it negative? And once they reach 7 consecutive negatives, they press retrain, and the process starts again until there are no positives on top. Again, this is heuristics, but it works really well for cleaning the data. And this is how the screen looks like. So we have the positive documents that we started from. We show, again, using the highlights, using, we don't need to save for later here because the set is already decided. And we just ask a simple yes-no question, something that's usually easy for the users. So we did these iterations of training, tuning, and now we're happy with the results. So what the user does now is to create a test set that they can evaluate the classifier performance. So we have 2 types of tests. Precision, basically, when I say, yes, this document is about the topic, in what percentage of the cases am I right? Is the classifier correct? And recall, how good is the classifier at capturing all the relevant documents? And we separate it to 2 tests because basically for the same reason that we created the query, because it's very hard just to rely on random samples of documents when the topics are sparse. So again, we ask the users to label documents, and here, after they pressed on the test button, run test, they can also look at the results. They can have here an analysis of the, in this case, the precision mistakes. So they see how many documents had errors in them and how many didn't have errors in them. And then they can try to understand what the model learned and how it should be improved, whether it's cleansing, expanding the query, adding some terms so that it has better coverage. And again, this is the part where they can also reach out and ask for our help. And in many cases, we can help them find some solutions to their problems. And once the results are good, the model can be deployed. So what we have is an engine called intelligent tagging. And this is a metadata extraction tool. And basically, with the click of a button, the user can publish it and have this up and running in the production environment. So I will show quickly how intelligent tagging looks like. So we have this document. This is about Revlon appointing a new CEO. So this is very relevant for this topic. And you can imagine that if I'm an investor and I invest money in Revlon, I would like to know about this story right away. So this is why it's important to find this topic. And once I feed this to intelligent tagging, I get a lot of highlights. So I get all the entities that are mentioned there, people, companies, relations between them. And I also have here topics. And one of the topics that was identified here is change of CEO. So, yay, the model did a good job, and we can be happy, and now users will be able to find this document. And one thing I wanted to say is that intelligent tagging is out and open. You can go and use it. Some of it is free of charge. So this is on permid.org. Please feel free to experiment with it. And again, you will enjoy the topics that our users are training. So I'll start summarizing. So this tool is used in Refinitiv currently by three different teams of content experts, which use different taxonomies and have different document types. And I'll show two graphs that I really like the story that they tell. So you can see here the number of topics that were published in the last year. Basically, a bit after we started working on this. So you can see that in the beginning, it was really slow, and it took a long time to publish topics. People didn't know how to use the tool. We didn't know how to guide them. The tool was worse than it is now, basically, in terms of user experience, in terms of algorithmic aspects. And now, in recent months, we already have 3 topics a month, which is really nice. And you can see that we already have 300 topics in production, so this is going quite well. Also, the time that it takes users to create a topic is decreasing. So we started from 26 hours almost a year ago, and now we're consistently on 13 hours per topic. So it basically, a user needs 2 days once they get a topic definition to go through all the cycle and click the publish button. And even if you think of data scientists, the time that it takes you to collect data, clean the data, write your solution, and write something that deploys it, I think this is really, really cool, and this is really, really exciting. And I promised to talk about alternatives to SVM, so this is an AI conference. I need to talk about deep learning. So as I said, our training sets are small. So most deep learning methods are not appropriate for them. And simple SVMs, even though they're outdated and old and not popular, they usually work better. But actually nowadays, so we have pre-trained contextualized word embeddings, Elmo and BERT, and if we combine them with hierarchical document representations, then we can get better results. So what do I mean by hierarchical document representations? And again, this, I think, from the algorithmic perspective, this is a simple but very cool idea. So I don't think that a lot of works look at this way, but this is from 2 years ago, a work from Microsoft, if I'm not mistaken. And basically, they say sentences are built of words, documents are built of sentences. Why don't we build the representation in stages? So we start from the words, we go over them, we generate representation of sentences, then we can focus on the important sentences using attention mechanism and get a representation of the document. And again, if we rely on already trained word embeddings, then we can get quite good results on small data sets like what we have. So this could be an alternative to SVMs, a good alternative to SVMs. But I think that still an SVM is a good baseline. We shouldn't shy away from using SVMs, even though they're not cool and they don't have as much hype as deep learning. And to reiterate the lessons that we learned, so first, what's really important is having good training data. You could be the best algorithms engineer, the best researcher, know the most about deep learning, but you need to have good training data. It should be as clean as possible, as comprehensive as possible. And then once you know what your data looks like, you can select the most suitable algorithm for it. So start from the data and then go into the model or into the algorithm. Secondly, it's not only the machines learning, it's the humans teaching. So we need to remember that we have people who know the content, who are experts, who have the knowledge, and we need to find ways to help them teach the machines. So in our case, define queries, provide feedback, do the error analysis. It's very important to use the help of the users to get from them as much as possible. And users have their limitations too. So users don't read long documents, users can't think of all the synonyms, users can't read thousands of documents, and we need to address these issues either algorithmically or from the UX perspective. So thank you very much, and I think we have time for questions.
So, Shai, thank you very much for this great talk. It was really, really helpful. Now we'll have, I think, time for quite a few questions. So let's go on with the first one. Due to long and boring process, any recommendations for auto-labeling or annotating images?
So I don't have any experience with image classification, only with text classification. I can say that what I didn't talk about, but we also experimented with, is active learning, basically guiding what document to show next to the user using the already existing classifier, and this can really reduce the training amount. Another thing, as you say, it's long and boring. If you have some attention mechanism or if you have a way to highlight the interesting area, then this is again something that could make the labeling more fun or more easy to do. And the final aspect is gamification. So we had some ideas, and we had some small experiments with doing some contests or having leaderboards, or we even had a small hackathon where people actually built games to help label documents. So again, this another way to make this less boring.
Mm-hmm. Mm-hmm. That's a great idea. And actually, for instance, because of the person, how do you tackle the subjectivity of the user, the third question over there, when training the algorithm?
Yeah, so that's a good question. I think in our case, it's less of a problem because, as I said, the users are content experts, so they really know the matter well, and I don't think they're very subjective when addressing this. In other problems, we just gave it to multiple annotators, multiple people, and then you can compare the answers and select the best one, and also calculate or compute the inter-annotator agreement, so you can know that the problem is hard or the problem is very subjective. And then, again, you can probably reiterate, refine the question, or refine the data.
Mm-hmm. Interesting. Okay, and also a bit more detailed question. So how do you handle multiple languages, or do you just look at English newspapers?
So that's a very good question. So we started from English, and now we also start to do some multiple language. So one way to do it is basically use the same solution for other languages, and it could work. You need to replace the way that you tokenize words, but this is really simple. What we can do if we want to do something more scalable, and this is really, really exciting and cool, is you can use translation services to translate the training data. And it turns out that if you take the training data in English and then you translate it to Japanese, and you use exactly the same algorithm and the training data was collected in the same way, you can have a Japanese model that's pretty good. And again, using some feedback mechanism, we can improve it and get a Japanese solution pretty fast for all the hundreds of topics that we already have. So
cool.
Not only English.
Cool. Okay, one last question. Did you evaluate your approach in comparison to other results in recent literature?
Yeah, so as I said, the comparison is hard because you usually compare only the model aspect. So you can replace the SVM with a different model and say, well, if I use ULM fit, then I get these results. And if I use the attention hierarchical representation, I get these results. But this doesn't cover all the problems. So if the problem includes the data collection, then it's much harder to compare. I think that, as I said, in terms of model, SVMs are good. They're not the best, but they're pretty close to the best, actually, for our data. And we're doing this model evaluation. So we are trying to find better models and to get even better results.